Hi, I'm Mark Barsamian. In this video, I'll be discussing topics from section 5.2 of the book. The first topic that I'll discuss is closed form expressions of sums. I'll introduce closed form expressions for two important sums, the sum of the first n positive integers and the sum of a geometric sequence. And then we'll use the closed form expressions of sums to find values for some particular sums. And then I'll use arithmetic to prove those closed form expressions for the sums that I introduced. And then I'll introduce what's called the principle of induction. That will be a new rule of inference, and that rule of inference, the principle of induction, can be used to prove the closed form expressions for sums. We'll prove one of the ones that was already proved earlier, that was proved using arithmetic, but then we'll prove one that is too hard to prove using arithmetic. All right, so closed form expressions of sums. I want to talk first about the sum of the first n positive integers. So it's well known that this equation is true. This sum is equal to this expression. Now, this sum is the first n positive integers. All of these numbers are integers. They start with the number 1, so starting with the first positive integer, and they're all consecutive all the way up until the number n. This formula is true for any value n greater than or equal to 1. So for example, consider this quantity, s. S is that sum. So question A, compute S directly by finding the sum. All right. Well, that equals, can do all these additions. There are 6 of them, and you get the number 28. Now, question B, we should compute S using this formula. So we got an answer of 28. Now, how many operations was that? It was 1 addition, 1 multiplication, and 1 division. So 3 operations. Of course, we used the fact that the number n was 7. Let's go on. Example 2. Consider this quantity. S is this sum. So question A is compute S directly by finding the sum. Well, that's too tedious. I can say how many operations that will be required to do that. It would require 199 operations. But again, it's too tedious. I refuse to do it. Question B, though. Find the value of S using this formula. Well, we have n equals 200. So using the formula, so there are 3 operations. We have an addition operation, a multiplication operation, and a division operation. So still 3 operations. And our value is 20,100. All right, let's go on. Sample 3, consider this quantity where n is unknown. Okay, well, question A, how many operations are required to compute S directly by finding the sum? Well, we don't know. It's whatever n is minus 1. Question B, how many operations are required to compute S by this formula? Well, that's 3. Now I want to talk about what are called closed form expressions. A closed form expression is a mathematical expression that involves a known finite number of standard operations. Notice that this expression contains n minus 1 operations. That is a finite but unknown number. So that expression is not a closed form expression. But this expression contains exactly 3 operations. So it is a closed form expression. This equation gives us a closed form expression for computing the value of a sum. That equation is useful because when n is known, the formula enables us to compute the value of the sum with fewer operations, like we did in these two examples. And when n is unknown, the equation enables us to replace the sum that has an unknown number of operations with an expression that has a known, a finite number of operations. Here's another equation giving a closed form expression that is equal to a sum. This is the formula for the sum of a geometric sequence. Remember that a geometric sequence is a sequence like this: 1, r, r squared, r cubed, and so on, all the way up to some r superscript n. Now a sum of a geometric sequence means that you take those terms of a sequence and you put pluses between all of them. So this is the sum of geometric sequence, this whole thing. So the formula that you can use to find the sum is this formula. So this equation says that that formula gives the same value as this sum. So for example, consider this quantity, 1 plus 2 plus 4, and so on, up to 64. So compute s directly by finding the sum. Well, we can do this. 64 plus 32 is 96. Add 16, you get 112. Add 8, you get 120. Add 4, you get 124. Add 2, you get 126. Add 1, you get 127. Now in question B, compute s by finding this formula, by using this formula. Well, so in this sum, our number r we can spot by looking at that first term, and the value of n we can spot by looking at the last term. 64 is 2 to the 7th power, so our n is 7. So we get the same answer, 127. Example 5, consider this quantity. Compute s directly by finding the sum, and then in question B, compute s using that formula. So to compute s directly, we just simply add up those numbers. We get an answer 15 over 8. To compute the value of s using the formula, we have to figure out what r is and what n is. Well, r is sitting in its usual spot, and n we figure out by scrutinizing the last term. We figured out that r is 1/2 and n equals 3, so now we can use those to compute s. So we just do standard arithmetic and we get the same answer, that s equals 15 over 8. Now I want to turn our attention to using the formulas for these standard sums to find values for sums that are not standard. So for example, find this sum. Let's give this sum a name. So notice that this sum consists of terms that are all multiples of 5. So let's factor out the number 5. So there we see we have inside those parentheses something that is almost the sum of the first 400 positive integers. Almost, because it's got a couple of terms missing at the beginning. So what we'll do here is a trick. We would like for the thing in the parentheses to be a standard sum, but it's not. So the trick is to put in some numbers that will make it a standard sum. So there you see I've just put in those two red terms, the 1 plus 2 plus, that will turn that into a standard sum. Of course I've messed it up because I've changed the value. So what I've got to do is I've got to subtract those terms that I added. So the trick here is that I did not change the value at all. I just added and subtracted 3 inside those parentheses. Now I'm going to break this up into two separate expressions. So I broke off that 3 into its own term. Of course, it's got to have a 5 multiplying it because on this line, there's a 5 multiplying that 3. Now, look, we have the sum of the first 400 positive integers. So we can use the formula for that. So on this line, I used that equation here to replace this expression, the sum of the first 400 positive integers, with this expression, 400 times 400 plus 1 over 2. Now we can do this arithmetic. We get a result that S is this number, 400,985. So again, we computed the value of a non-standard sum by rewriting that non-standard sum in a way that we could spot the form of a standard sum inside the expression. And then we used the formula for the standard sum. Let's do another one of those. In this example, we'll find this sum. That's a non-standard sum. Well, let's start by giving this sum a name. Now, it's hard to see right off the bat what to do with this. One thing that you can notice, though, is that each one of these numbers is even. So let's factor out a factor of 2. Now notice that the first 3 terms inside those parentheses are powers of 3. So it's a good guess that 6561 is probably also a power of 3. It's not hard to figure that out. The result is that this number, 6561, is 3 to the 8th power. So look, that thing in parentheses looks almost like a standard geometric sum. But it's missing a couple of terms at the beginning. It's missing the number 1 and it's missing the number 3. So in the next step we can do a trick. We can just put those numbers in. Of course, if we put those numbers in, we have to correct for that by subtracting them as well. So we added in a total of 4, so we have to subtract 4. So there's our trick. We added 4, subtracted 4. And the result is we've created an expression that is a standard geometric sum. Let's rewrite this so that term is by itself. So what we have here is the standard geometric sum with r equals 1 and n equals 8. So we can use the formula for a standard geometric sum. Let's go up and remind ourselves how that looks. This geometric sum equals the value given by this formula. So we need to build one of these in place of that. The result is that we have a value of 19,674 for this sum. Now I want to talk about using arithmetic to prove the closed form expressions for sums. Some closed form expressions can be proved easily using arithmetic. So for example, we can prove this formula, the formula for the sum of the first n positive integers. The way this works is we're going to give this a name. We're going to call that quantity S. Now I want to do a trick. I want to write 2S, but I want to do it in a tricky way. You see, I've written out the expression for S, and I've unhid a couple of terms. Now I have to write it down again, because I have to have S plus S, but this time I'm going to write it backwards. So there's my sum, written in this kind of crazy way. Now I want to compute this value. I'm going to add these terms pairwise as follows. I'm going to add these two. That's going to give me n plus 1. Then I'm going to add these two. And that's going to give me n plus 1. And so on, all the way to the end. Every time I add one of these pairs, I'm going to get n plus 1. So for each of these vertical columns, I'm going to have an n plus 1. Now, how many of those do I have? Well, you can see I have, starting with 1 all the way up to n, I have n of these things sitting side by side. So I can rewrite this as n times n plus 1. So 2s equals n times n plus 1. So that means that s equals n times n plus 1 over 2. So we've proven our formula. And notice we just used arithmetic. Example 8, let's prove the formula for the sum of a geometric sequence. We want to prove that this equals this. Well, I'm going to do the same thing. I'm going to let this sum be denoted by the letter S. Now, if that's S, notice that I can multiply that by R to get the following. Every power gets raised by 1. Now, I can do this subtraction, RS minus S. Now I'm going to stack these above each other. There's my expression for RS. Notice that I have unhid one term. That term was hidden in that ellipsis, in that dot, dot, dot notation. It's been revealed here. I unhid it. But what I have so far is just simply RS. Now I'm going to, on the next line down, write the terms for the sum S, and I'm going to move them over. So there are the terms for the sum S, and you can see that I move things all over. Now I have to subtract the things on the bottom row from the things on the top row. Now you can see that the R in the top row is going to get canceled by that R in the bottom row. And that R squared in the top row is going to get canceled by that R squared in the bottom row. And so on, all the way down to that term. So what's going to be left is that. So on the left side, notice the left side can be written as S times the quantity, R minus 1. So I end up with this expression. That's the right side of that equation. We've shown that this sum equals that expression. So we were able to prove both of these formulas for closed sums, this one involving the geometric sum and this one involving the sum of the first n positive integers. We were able to prove both of those closed form expressions using just arithmetic. But many equations that involve closed form expressions for sums must be proven using what's called the principle of induction. So that is a new rule of inference, the principle of induction. And here's how it goes. It is this rule of inference. So remember how rules of inference look. They have hypotheses and conclusions. So one hypothesis is that P parentheses A is true. The second hypothesis is this whole thing. For all integers k greater than or equal to a, if P of k is true, then P of k plus 1 is true. That's the second hypothesis. Then the conclusion is this sentence. Therefore, for all integers n greater than or equal to a, P parentheses n is true. So that's quite a mouthful. Now, what are the parts of this? What's the usage? Well, the letter A represents some fixed integer. The letters k and n represent variables whose domain is the set of all integers greater than or equal to a. And then the symbol P parentheses n represents a predicate. Now, what do we do with this? Well, one clue is this. This rule of inference ends with these words. Therefore, for all integers n greater than or equal to a, P of n is true. Well, that means that we can use this rule of inference to prove statements of this form. For all n greater than or equal to a, p parentheses n is true. But this is quite a mouthful of words and symbols. So how are we going to use this rule? Well, I want to discuss the strategy. When you're going to use this principle of induction, you need to do some preliminary work. You need to identify the number playing the role of a. You have to introduce it. You have to identify the predicate, p parentheses n. Introduce that in a sentence. And then figure out what the expressions for p parentheses a, p parentheses k, and p parentheses k plus 1 look like. Write them down. So I'm just going by what's mentioned in this rule of inference. The symbol a is there. The predicate p parentheses n is there. P parentheses k is there. P parentheses k plus 1 is there. P parentheses a is there. All of these things are mentioned in this rule. So we have to make sure that we know what those things are before we can think about building this argument. Now, once we have those things done, that preliminary work, what do we do next? Well, we have to build a proof using the structure that's specified by that rule of inference. Let's go back up and look at the structure. This rule of inference has two hypotheses. One is p parentheses a is true, and the other hypothesis is this great big statement. So if we're going to do a proof using this principle of induction, we're going to have to, in our proof, have this thing and also have this thing. And finally, we would end our proof with the conclusion. Therefore, for all integers n greater than or equal to a, p parentheses n is true. So these three things are going to be in our proof. So when we build our proof, it's going to have that first thing, prove that p parentheses a is true. That's going to be called the basis step. That's that thing. The next thing is to prove that for all integers k greater than or equal to a, if p parentheses k is true, then p parentheses k plus 1 is true. That is that second thing in the rule of inference. But how do we do that? How do you prove something like that? Well, notice that that's a universal conditional statement. There's a universal quantifier, and then there's a hypothesis, and then there's a conclusion. So if we want to prove this, we will use the method of direct proof. So we say, suppose that k is an integer, such that k is greater than or equal to a, and also suppose that k greater than, this is a typo, this should say p parentheses k is true. So here we have that hypothesis put down here. And so this is the generic particular element. We have an element of the domain that satisfies the hypothesis. So that's how the structure of a direct proof starts. How does a direct proof end? Well, remember, it ends with whatever's sitting here. So this proof has to end with that red statement. That's the conclusion. So this whole thing is a direct proof of this middle step called the inductive step. And that's that second thing that's mentioned in that principle of induction. The principle of induction has this hypothesis. So that hypothesis needs to be proved in our proof. And it's going to be proved using this structure of a direct proof. Now, in this proof structure, this whole sentence is one of the hypotheses in the principle of induction. That whole row, that whole sentence is that hypothesis. Within that sentence, there's another hypothesis here. This is a hypothesis for that conditional statement. So we have a conditional statement here. If P of k is true, then P of k plus 1 is true. And for that conditional statement, that green circled statement is the hypothesis. So this green circled statement is called the inductive hypothesis. That green circled statement is the hypothesis for that blue circled conditional statement. And that's part of this whole step, which is one of the hypotheses for the proof. So once we do that, once we have this inductive step completed, that's the second line of that principle of induction. Let's go back up and look at the principle of induction. The third line of the principle of induction is this thing, the conclusion. Therefore, for all integers n greater than or equal to a, P of n is true. So our proof using that principle will end with that conclusion line. Therefore, for all integers n greater than or equal to a, P parentheses n is true by the principle of induction. Let's use this to prove something. Let's use the method of induction to prove the formula for the sum of the first n positive integers. So we've already proven this. This is this equation that we've already got verified. But let's prove it again using the principle of induction. Let's set up the proof. First of all, let's do the preliminary work. Remember the preliminary work. Identify the number playing the role of a, identify the predicate P parentheses n, figure out these expressions, write all that stuff down. So a is the number 1. Whatever number appears in that inequality is the value of a. Now we need to identify the predicate. And then what else? We need to identify P parentheses k. P parentheses k is going to look just like P parentheses n, except all the n's are going to be replaced by k. And then we need to write down P parentheses k plus 1. So there you see we've got our P parentheses k plus 1, which we obtained by simply replacing all of these n's, that one, that one, that one, with k plus 1's. That one, that one, that one. Okay, now we have the preliminary work done. Now we're ready to build the proof. So we have to have the first part of the proof has to be the basis step. Remember what happens in the basis step. We have to prove that P parentheses a is true. All right, well, remember what P parentheses a is. Oh, we didn't write that down up here. We didn't do all of our preliminary work. So to build the predicate P parentheses 1, you write down this equation, replacing all of the n's with the number 1. So there's the statement P parentheses 1. Now that looks kind of weird. We talked about this in a previous video. That's a statement that uses ellipsis to describe a sum, but in the case when you have a number here that's smaller than these numbers, it's a little confusing. Remember what this means. This means to add up a bunch of numbers that look like that pattern, starting with that one and ending with that one. Oh, well, if it's going to start with that one and end with that one, that means that this sum is only going to have one term in it. So this is actually just this. So there is P parentheses 1. Now, P parentheses 1 is not a number. It's not the number 1. It's a statement. It's the statement that says 1 equals 1 times quantity 1 plus 1 over 2. So it's a statement. It's a statement that's either true or false. Let's go back. Notice that P parentheses n is a predicate. It contains a variable n. It's neither true nor false until we substitute an actual value of n in. But P parentheses 1 is this actual statement. Okay, now let's go back. We have to prove that P parentheses a is true in the basis step. So there's the equation that's p parentheses 1. Now we have to prove that that's true. Well, let's just simplify this. That statement is obviously true. So that's the sort of thing that often happens in the basis step. Remember that the basis step is where you come up with that first hypothesis for the rule of inference. We have to prove that p parentheses a is true. And it always involves some computation, because you're actually finding out if a particular statement is actually true, and it can take some steps. So we've done the basis step. Now what's next? Well, we have to do the inductive step. We have to do this whole thing. So we have to set up a proof of this using this direct proof form. So in the inductive step, we're proving this universal conditional statement. So we set that up with a direct proof. So the direct proof structure is we start with a generic particular element, something that's in the domain and satisfies the hypothesis. And remember that this hypothesis is the inductive hypothesis. And remember how this direct proof structure has to end. It has to end with this. So that's the frame of the direct proof. Now notice we've got some stuff that we don't have any choice about. We have a defined expression, p parentheses k, so in step 2 we have no choice but to write out what that means. And look at the very end of the proof. We end with this, p parentheses k plus 1 is true. We have no choice about that but to write, to have preceded that statement with what that actually means. So we have to get to here in order to say that p parentheses k plus 1 is true. Now we're supposing that this one is true. That's the inductive hypothesis. But we have to prove that therefore this is true. So there's our gap that we've got to bridge. We've got to somehow get from statement 2 all the way down to this statement. Well, how do we do that? Well, we can start by doing this. We can build the left side of this equation and then see if it equals the right side of this equation. So I'm going to make some space by moving what we've written down onto the next page. So there's the gap that we have to fill. We have to get from this line, which is the inductive hypothesis, down to this line, which is the statement that p parentheses k plus 1 is true. So what I'll do is I'll start by building the left side of p parentheses k plus 1. So there you see is the expression that's on the left side of p parentheses k plus 1. That expression. Now I'm going to do a trick here. I'm going to unhide one term. You see that this term was hidden in that ellipsis. The reason for doing that is you recognize that this stuff is the left side of pk. But pk is true. That equation is true. So that left side, this stuff, equals this stuff. So p parentheses k tells us that whenever we see one of these things, we can replace it with one of these things. So I'm going to do that in the next line. So we replaced this green stuff with this green stuff, and that is using p parentheses k, that is using the inductive hypothesis. So we're assuming that pk is true. We're supposing that it's true. So it allowed us to make that replacement. Now look, we've got to add these two things together. They don't have a common denominator, so we've got to work on that. We've got to get a common denominator for the second term. So I got a common denominator by multiplying the top and bottom of that by 2. And now look, we can combine these fractions. Now at this point, we should look ahead to see where we're going. Well, where we're going was we started with the left side of p parentheses k plus 1, and we're hoping to get to something that looks like the right side of p parentheses k plus 1. So we're hoping to find something that looks like this. Look how close we are. We've got this. We want this. So let's push on and let's factor what we've got. So there you can see that what we've got is the right side of p parentheses k plus 1. So let's recap. We started by writing down the left side of p parentheses k plus 1, and we ended up showing that it's equal to the right side of p parentheses k plus 1. So in other words, we showed that this equation is true. And we were only able to do that because in the middle we used this inductive hypothesis, p parentheses k. Now notice we never did prove that p parentheses k is true. We just assumed that it's true. We said suppose it's true. If it is true, then p parentheses k plus 1 is true. So we have shown that therefore p parentheses k plus 1 is true. But again, we only did this contingent on the idea that p parentheses k is true. We said if p parentheses k is true, then p parentheses k plus 1 is true. So that's the end of the proof of the inductive step. So now what's next? Let's go back up and look at our proof structure again. We need the last thing. We need to have this conclusion. That was the concluding line of the principle of induction. There's that rule of inference. We've done the basis step. We've done the inductive step. Now we have to write the conclusion. So there's our conclusion. For all n greater than or equal to 1, this equation's true by principle of induction. So we've got all three components of the proof. We have the basis step, we have the inductive step, and then we have the conclusion. That's the end of the proof. Now, this is remarkable. Again, I want to draw your attention to the fact that the only case that we actually proved was true was p parentheses 1. We proved that p parentheses 1 is true. We didn't prove that pk is true. We didn't prove that pk plus 1 is true. We only proved that if pk is true, then pk plus 1 is true. But we didn't prove that either one of them is true. We just said if that one's true, then that one's true. That's what goes on in the inductive step. And then the amazing thing is we get to write this conclusion. So we've proven that for all integers n greater than or equal to 1, that equation's true. So that's our first proof using induction, and it took a long time. Now I want to discuss another proof. This proof that we just did is actually presented in the book on page 280. It's a theorem, theorem 5.2.1. There's another nice proof using induction in the book as well. In the book, theorem 5.2.2, they prove this, which is the formula for the sum of a geometric sequence. Remember, we proved this formula without using induction, just like we proved the formula for the sum of the first n positive integers. So the example that we just did and this example that's done in the book are two examples that can be done nicely using induction, but it's super hard. It's kind of silly to do it that way if you can do the proof using just arithmetic, but they're good examples to start with for induction, so you get the sense of how to use the method, and then you recognize the result. But I would like to do one more example to use the method of induction to prove a formula for the sum of the first n positive perfect squares. So here we have a sum, and each of these numbers is a perfect square. We're leaving out the perfect square that is 0 squared. That's not on the list. So this is the first n positive perfect squares. So there's a neat formula that says that sum of those first n positive perfect squares is equal to this messy formula. Well, this is one that looks a lot like the one we did earlier for the sum of the first n perfect squares, first n positive perfect squares. But this is one that we can't prove using simple arithmetic. So we have to use induction. So here we go. Let's do the preliminary work. We identify our A. A is the number 1. We can spot that by looking at that inequality. We have to identify our predicate. That's our predicate, P parentheses n. We have to identify P parentheses A. So P parentheses 1 is simply substitute 1 into this expression everywhere there is an n. So we substituted the number 1 in 3 different spots. Now, this is not very helpful. What does that really mean? That just means the number 1 on the left side. So there's P parentheses 1. Remember, P parentheses 1 is not a number. It's not the number 1. It's this statement. This equation is a statement. That's P parentheses 1. We're supposed to do some other stuff as part of the preliminary work. We're supposed to identify P parentheses K. So I simply got the expression for P parentheses n and replaced all the n's with k's. But we also need to get P parentheses k plus 1. Now, it will help greatly if we simplify this expression a little bit right now. So let's write P parentheses k plus 1 a little bit more simply. So I rewrote the right side. Instead of k plus 1, I wrote k plus 2. And instead of 2 parentheses k plus 1, I just wrote 2k plus 3. So this is P parentheses k plus 1. All right, now we need to build a proof. So we're going to use the method of induction. So we start with the basis step. Remember what happens there. We need to prove that P parentheses A is true. Well, P parentheses A is P parentheses 1. And P parentheses 1, remember, is an equation. It's this equation. So we've proven that P parentheses 1 is true. And again, P parentheses 1 is not 1. It's the statement. 1 equals 1. That's a statement. It's a true statement. It's not a number. So that's the basis step. The second thing we need to do is the inductive step. Remember what happens in that step. We have to prove that for all k greater than or equal to a, if P parentheses k is true, then P parentheses k plus 1 is true. So we do a proof using the direct proof structure. So we start by introducing a generic particular element, an element that satisfies, that's an element of the domain and that satisfies the hypothesis. And that's the inductive hypothesis. Now that's the start of a direct proof. The ending of the direct proof has to be this red statement. So there's our frame of a direct proof for the inductive step. Now we have some stuff that we have to deal with. P parentheses k is true. That's a defined expression. So we should follow that up with what that really means. And At the end of the proof, we have this red statement, which is the conclusion of that if-then, and it has this defined expression, p parentheses k plus 1 is true. So backing up one step, in order to get to this black statement, we're going to have to have previously shown this. Now, what was the other side of that equation? This stuff, which was simplified to this stuff. So that's the right side of p parentheses k plus 1. So that's where we need to get to. We have to bridge this gap. Now, to do this, I'm going to need some more room, so I'm going to move a bunch of stuff down to the next page. Okay, so there's our frame of the direct proof for the inductive step. Now we need to bridge this gap. Now notice what we're trying to get to is this equation. This is the left side of p parentheses k plus 1, and this is the right side of p parentheses k plus 1. Well, let's go back up where we are, and let's resume by starting with the left side of p parentheses k plus 1. Let's work with that and see what we can do with it. See if we can show that it really is equal to the right side. So the left side of p parentheses k plus 1 is this sum of a bunch of perfect squares going all the way up to that one. So I want to do what we did in the previous example. I want to reveal a term that's hidden. So this term was hidden in that ellipsis before. It was there, it just was not being shown. So it's being unhid, it's being revealed. So what we're looking at there is still the left side of p parentheses k plus 1. Oh, but look, in that expression, we spot that. That's the left side of p parentheses k. That's that stuff. Now p parentheses k is true. We're assuming it's true, so that left side equals the right side of p parentheses k. In other words, whenever I see one of these, since I know that pk is true, or since I'm assuming that pk is true, I can replace that with that. So I replaced all of that stuff there with this stuff, so I use the fact that pk is true. Now notice, we did not prove that p parentheses k is true. We just are assuming that it's true. Well, let's go on from here. Look, we want to simplify this, so let's get a common denominator. Okay, that'll help. Now, I'm going to need some more room. Actually, I'm going to move some stuff down to the next page. I'm going to grab this stuff. Actually, I'm just going to move it down to the bottom of this page. So we're trying to get to something that looks like the right side of p parentheses k plus 1, which is this stuff. One great big fraction with a 6 on the bottom. So I'm going to combine these terms. Now I'm going to distribute this k into that term. Over here on the right, I'm going to do something sneaky. I'm not going to multiply this out. The reason is, if you look ahead, the thing that we're trying to get to match has a k plus 1 in it. So I want to leave my k plus 1 as a factor. So I'm going to write that way. And furthermore, I'm going to distribute that 6 here and here. So look, I've got a k plus 1 there and also there. I want to have a k plus 1 as a factor, so I'm going to factor that out. What does it leave behind? It leaves behind 2k squared plus k plus 6k plus 6. All that's over 6. But that's can be simplified further. And that can be simplified further. I'm going to move this stuff down out of the way. So I factored this expression to get this. How did I know to factor that? Well, I looked ahead to where we needed to go. We knew we needed to have those factors, so looking at this red circled expression, I sort of had a clue as to how it was going to have to factor. But you can confirm that those factors are right. So now you see that what we're looking at here is the right side of p parentheses k plus 1. So let's refresh ourselves on what we did here. We wrote down the expression that's the left side of p parentheses k plus 1. We worked on rewriting it, and we ended up with an expression that's the right side of pk plus 1. So we showed that those were equal. Along the way, we had to use the fact that p parentheses k is true. So we didn't prove that pk plus 1 is true. We didn't prove that pk is true. What we proved was if you assume that pk is true, then pk plus 1 is true. So we proved that. So we've shown that this equation's true, so therefore p parentheses k plus 1 is true. Again, this is contingent on assuming that pk is true, and so that's the end of the proof of the induction step. What's next? Well, let's go back up and review our proof structure. We've done the basis step, we've done the inductive step, so now we're just left to write the conclusion. The conclusion is, therefore, for all integers n greater than or equal to a, p parentheses n is true. So there's our conclusion. Again, our proof has three parts. The basis step, the inductive step, and the conclusion. Because that principle of induction, that rule of inference, had those three lines. So that's the end of this very long proof of this example. So again, these induction proofs take a long time, but I think you can see this second one that we did went a little bit faster than the first one. So the idea of this is that you want to practice as many of these as you can. All right, well, that's the end of this video. Thank you.